This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome back to Chapter 3 of our series, Simulating Space Environments in Your Lab. In this episode, titled Radiation and Particle Simulation, we'll explore the fascinating world of space radiation and the different types of particles that fill the cosmos. So, get ready to expand your knowledge and uncover the secrets of the universe. Let's dive in. Right now, above your head, space is firing a constant storm of invisible bullets at Earth. Most never reach you, but step outside our magnetic shield and that protection vanishes. Here's the twist. To keep astronauts safe, scientists first have to build artificial radiation on Earth. Out in deep space, that radiation storm isn't just a health problem, it's also a relentless hardware stress test. Every spacecraft computer, sensor, and memory chip is sitting in a firing range it can't step out of. And here's where things get tricky. Real cosmic radiation is messy. It's not one clean beam, but a shifting mix of protons, alpha particles, and rare heavy ions that can each do damage in very different ways. To predict how this chaos plays out, scientists turn to two powerful tools: Monte Carlo simulations that track billions of possible particle paths, and accelerator facilities that hurl precisely tuned beams at living cells, metals, and microchips. By bouncing between code and accelerator halls, they gradually turn a wild, random space hazard into something we can model, measure, and, eventually, design against. On Earth, our baseline is deceptively calm. Natural background radiation trickles in at levels our biology and electronics can usually shrug off. Step into deep space, and the numbers jump fast. Galactic cosmic rays alone add roughly 0.3 millisieverts per day, before flares or solar storms pile on more. That shift matters because not all particles are equal. A rare heavy ion plowing through a cell can shred thousands of DNA bases in one pass, while a similar hit in a memory chip can flip a critical bit. The challenge is to reproduce these rare, extreme events often enough in the lab to learn from them. Start with the numbers. Outside Earth's protection, astronauts rack up about 0.3 millisieverts of dose every day, whether they do anything or not. That value hides a messy spectrum of particles and energies, so the first job in the lab is to unpack it into something programmable. Monte Carlo codes like Geont4 begin by ingesting detailed inputs: spacecraft geometry, human body models, material compositions, layer by layer. Then they fire virtual particles at this digital twin by the billion, recording where energy is deposited, what secondary particles are born, and how often a critical component is hit. Over time, this produces 3D risk maps of a habitat or suit. Hotspots where ions tend to focus, dead zones where shielding quietly works, and weak points where small tweaks in layout could halve the dose to a vital organ or a vulnerable chip. But software alone can drift from reality. That's where accelerator data comes in. Facilities such as NASA's Space Radiation Laboratory can sweep through different ion species in under half a minute, building composite exposures that better approximate the complex mix beyond low Earth orbit. Biologists use those beams to measure how often chromosome breaks, cell death, or mutations occur at specific energies and ion types. Engineers, in parallel, probe electronics. How many single-event upsets per fluence? How latch-ups scale with voltage? How shielding or error-correcting codes change the failure statistics? Mixed-field setups like CERN's CHARM go one step further by bathing hardware in broad, time-varying radiation fields. There, entire subsystems or racks are operated under realistic loads while the beam reproduces, in an hour, the neutron environment that satellites experience over a year in orbit. Logs from these stress tests feed back into the models, tightening predictions for future missions. The interplay works both ways. Simulations suggest which particle types and energies matter most. Accelerators then target those zones for focused experiments. Iterating between the two gradually replaces rough safety margins with quantified tolerances. How much shielding mass is actually worth flying? How far a habitat needs to be from a cargo bay full of secondary particle-spawning materials? And which robotic scouts or relays can accept higher error rates to save cost and weight? Bit by bit, the seemingly random radiation background becomes a design parameter, something mission planners can trade, optimize, and test on the ground long before hardware or humans leave it behind. At NSRL, for example, a biology team might spend a morning stepping through a sequence of beams that mimics a Mars transit, then freeze their cell cultures and ship them to a genomics lab to look for subtle mutation patterns that wouldn't show up in short-term survival tests. Down the hall, material scientists stack candidate shield panels, polymer composites, hydrogen-rich plastics, even 3D-printed regolith bricks, and rotate them through the beam to see which ones spawn the fewest nasty secondaries. Over in Europe, charm staff roll in whole flight computers, power units, and star trackers, run them with realistic software loads, and log every glitch, reset, and silent bit flip for months of equivalent orbital time. One analogy helps here. These campaigns are like architects stress-testing skyscraper designs in an earthquake simulator, trying different structural layouts and dampers until the invisible forces become measurable and, crucially, negotiable design trade-offs. As models tighten, mission planning starts to look less like guesswork and more like weather routing for ships. Crews might time departures to calmer radiation seasons or choose slightly longer trajectories that skirt stormier regions. Data-driven dose forecasts could personalize bunk locations, workload, and even drug regimens. On the ground, the same tools may quietly shape hospital layouts, drone flight corridors, and data center designs, where stray particles already nibble at our increasingly miniaturized electronics. Bit by bit, we're turning radiation from a mysterious threat into a parameter you can tune, like clock speed in a processor. As these tools mature, expect space habitats that route particle traffic, chips that self-heal after hits, and medical scanners calibrated with the same physics that shields a Mars crew. One unified playbook for surviving high-energy worlds. Here's your challenge this week. Install a free or community radiation/particle simulation tool like JAUNT4, MCNP demo/tutorial environment, or a web-based Monte Carlo simulator, and run one simple scenario where you simulate a radiation source passing through at least two different materials, for example, water versus lead. Change exactly one parameter, such as particle energy, material thickness, or shielding material, and record how the dose distribution or particle attenuation changes numerically. Finally, write a 3-sentence lab note explaining which setup reduced exposure the most and what that suggests about real-world shielding design. This was OwlUp, your daily step forward. This series continues with more chapters on OwlUp.co. Visit OwlUp.co to access the complete course and continue your learning journey. See you there!